In this lesson, we are going to recap lessons 4.5 and 4.6 of honors chemistry. But before we begin with that, I'm taking a trip to southern Florida in December, late December. I don't know what I'm doing exactly, but I know I'm going to be going to Fort Lauderdale, to Miami, to the Everglades. I'm seeing an NBA game. Pick one activity, and I can make a small clip from the activity that I'm doing in South Florida in the comments. And whatever I think is the best suggestion, I'll make a video on that. But if I don't get any comments, I don't know what videos I'm going to make, and it might not exactly be something that you want to see. So just a thought, you might want to put it in the comment section below. But lesson 4.5 is actually about light in chemistry. So this is where chemistry begins to take a bit of a turn into physics. And also in chemistry honors, it touches on like biology and geology concepts, but this is where chemistry begins to intercept with physics a little bit. I just need to get to my own copy that I made because there is math in this. There are mathematical equations that we had to write down, and I'm not really going to show you through them, but you should probably see it. So, Sir Isaac Newton, made the particle theory. He's a famous physicist that suggested that light consisted of tiny particles, and the wave phenomena was that light traveled as waves. In the early 1900s, Max Planck revived the particle theory, saying that light is made up of discrete bundles of energy. A quanta is bundles of energy, so I need to fix that in my lab report, and the amount of energy in each quanta is related to the color of light. The dual nature of light is that light can behave both as a wave or as a particle. De Broglie suggested that if light can have both wave-like and particle characteristics, that particles can also have wave-like characteristics. Electrons can produce different the diffraction patterns, which is associated with waves. This is what a wave looks like. The wavelength is the difference between crests or troughs, and the amplitude is the height of the wave. The frequency is the number of wavelengths per unit of time. That is another transverse wave. The speed of light is 3 times 10 to the 8th meters a second. That is an approximation. As you can see, there's only one significant figure here. I'm just going to touch upon significant figures really quickly. Significant figures is the number that determines precision. So like when you do math, you always round to the lowest amount of significant figures. You just like always do that, because otherwise you run the risk of having false precision. In some cases, this might not be applicable, and you might not do enough. So if you have like a 0, for example, you have a period. Like, for example, that number 85.0, there's a decimal and a 0 after it, so it's 3 significant figures. If you had an 85 with nothing after it, it would only have 2 significant figures. And that would mean that I could go from anywhere from like 84.5 to 85.5. With that, it's between 84.95 and 85.05. So it's more precise, but it's not perfect. It's not like 28 significant figures or something like that. So just so you know, that's about a little bit about significant figures, and you only have one significant figure. I think it's like 2.998 times 10 to the 8th in reality. So wavelength and frequency are inversely related. And that makes sense, because if you have a longer wavelength, it can't run as frequently. So you have C equals gamma V. Oh no, C equals lambda nu. So the speed of light is equal to the wavelength times the frequency. So in this case, to find a wavelength of a blue light with a frequency of 8.3 times 10 to the 15 hertz, it would be 3.6 times 10 to the negative 8, and that's the math behind that answer. The other stuff is a little bit incomprehensible because I actually typed it up and I didn't organize it properly. The continuous spectrum is when white light is separated into a band of colors. Colors range from red to violet, and you use the prism. This is where Voight-Biv comes into place. The closer to red, you have a long wavelength, low frequency, low energy. The closer to violet, short wavelength, high frequency, high energy. The bright line spectrum is in incomplete colors, which are characteristic of the metal. It can be used to identify the substance. It's the fingerprints of the element. Each element has its own unique set of lines. Solid salts in solution also give off colors. Why? It's because of the excitement of the atoms. It causes electrons to jump to the higher energy bands. Upon the return of electrons to lower energy levels, the energy that was associated is released in some form of visible light. This is where light and chemistry intertwine. Get ready for the marriage between physics and chemistry. Light is released in small pockets that are called photons. Photon energy is directly related to the color of the light. The bright line spectrum is produced as a result of electrons falling back from higher energy levels to lower energy levels, from excited to ground. This is just you can drag the lines down to determine what the unknown mixture is and what gases would be in it. You have to do an exact thing. Now for the final concept of 4.5, and we're doing both 4.5 and 4.6, we have electromagnetic radiation. Visible light is only one type of radiation. We have gamma rays, X-rays, UV, infrared, radar, microwaves, and radio waves. Radio wave is not necessarily one of the waves that we learn. So when you look at how tiny the visible light spectrum is, it's literally just this narrow row. And as you see, it goes radar waves, then radio waves, and radar, microwaves, infrared, visible light. Then you have ultraviolet rays. UV rays are, of course, the ones you get from the sun for not using sunscreen because they have a higher frequency. Then X-rays, and that's why they have like all that equipment. When you get an X-ray, they have to have that because the X-rays can actually seriously mess you up, and sunscreen won't be enough. Gamma rays have such a high frequency that they can kill you, but they're also used as some kind of cancer treatment. And we didn't really learn that, but if you want a little bit of a mix between bio and chemistry, it's not biochemistry, but it is a mix between biology and chemistry if you wanted that. Lesson 4.6 is the Bohr model. So there's math in this as well, so we have to go into the long PDF format. This one is also 10 pages. These are long lessons, so this is going to be a pretty long video for a chemistry video because I'm combining two of them. The Rutherford model is positively charged nucleus surrounded by negative electrons. There are some shortcomings of it though. If the electrons are stationary, they should be drawn into the positive nucleus. If the electrons orbited the nucleus, they should have radiated electromagnetic energy. So Niels Bohr in 1912 made the Bohr model. An atom is similar to the solar system. Electrons orbit the nucleus in concentric orbits, circular orbits at a fixed distance from the nucleus, and electrons in a specific orbit have a specific amount of energy. The greater the radius of the shell from the distance of the nucleus, the greater the energy for the electron. This is called principal energy levels. Just going to make it so you can see it a little bit more clearly. So, in case you're wondering about why they have to have higher energy, so it's all about the distance. Like, if you have to, in a second, transverse, say, 10 feet, because that's your distance, that's your radius. Actually, no, it would be like 10 pi feet. So 31.4 feet. If your radius is 50, you have to do 50 pi feet, which is about 157 feet. So it's going to obviously be, you're going to have to go 5 times faster if you're farther from the center, and that's how electrons work. It's not a solid material and represented the most probable location in space where an electron can be found. They don't actually have these fancy orbits. It's just made like this. They were initially denoted by letters K, L, M, N, O, P, Q. Why is it started K? I have no idea. Each energy level can only hold a specific amount of electrons. So in a ground state, an atom is where the lowest levels are occupied. Atoms can absorb energy from an outside source, like heat or voltage. An absorption of energy causes one or more electrons within the atom to move to the higher energy levels into the excited state. An atom is where one or more electrons are occupying a higher energy level than available. Is it stable? No, they're unstable, and electrons will quickly return back to the lower energy levels. when I say unstable, I'm pretty sure it doesn't have like radioactivity in it. Radioactivity is when the elements begin to decay. There are a bunch of elements that always decay, and some have certain isotopes that decay. I was looking it up today, and the most radioactive element is actually hydrogen-7, which when you think about it, if hydrogen-3 is really unstable and is used to make a hydrogen bomb, it's really rare too. Then imagine how unstable hydrogen would be if you have 6 neutrons in it. It wouldn't work. It's so unstable, it's the shortest half-life. Francium is the element that has the shortest half-life of like the longest one. Because as you know, hydrogen-1 is stable. But once the nucleus just gets too large and the element just gets too large, it'll be radioactive and it's going to decay. But this isn't exactly what they mean, although an unstable element is a radioactive element. So the quantum state is the amount of energy needed to raise an electron from one level to another. The same amount of energy is released when the excited electron returns back to ground state. E equals hv, so energy equals the Planck's constant of 6.63 times 10 to the negative 34 joules a second times the frequency. For this is a 2-part problem, and you can see all my chicken scratch. Same for here. But the energy of photon E is equal to h times c over lambda. If you want to do like that complicated thing, like another PV equals nRT kind of thing. So K to L, L to O, M to P are going to absorb energy. P to N, L to K, O to L are going to release energy. And as you can see, the closer to the nucleus you get, the bigger the distance between the shells are going to be. So K to L is going to be bigger than L to M. The spectral lines are the results of electrons falling from higher energy levels to lower one. There is a shortcoming of the Bohr model. It worked well for hydrogen with 1 electron, but did not work for any other atom, including helium, with 2 electrons. So as far as the atomic spectra goes, this is when it moves from the ground state to the excited state. It must absorb energy. This emits energy and is the basis of atomic spectra. That's atomic spectra. As far as how many shells that can be held in each row, it's 2a squared, a being the amount of rows. So in K, it's going to be 2, L is 8, M is 18, N is 32. And this is kind of what it's going to look like. Now, I know what you're wondering is like how there's only 8. And unfortunately, my chemistry teacher actually refused to answer that question today. So until next week's video, and I don't even know what lesson it's going to be, we won't actually be able to talk about why they're not completely filled, because I don't even know the answer. But I do hope that you enjoyed my very long chemistry video.